Welcome to today's lesson on average and instantaneous rate of change. By the end of the lesson, you should be able to understand the definition of average rate of change and its connection with the slope of a secant line. You should also be able to use this definition to actually calculate the average rate of change for a function or a given set of data. And you should understand the connection between the average rate of change over a very small time interval and the instantaneous rate of change at a point. Okay, let's begin. What I have here is some temperature data that was recorded at regular time intervals, and from this I can calculate the average rate of change. You may recall what this is. It's just the change in the y values over the change in the x values. Or, some of you may have seen, the rise over the run. Okay. So we could do that by picking some x values. So let's call this t1 and this one t2. So time interval t1 to t2. And let's take this as capital T for temperature, 1, and T2. Then the average rate of change over this time interval is just delta T, so the change in big T, over delta small t. So that's just given by T2 minus T1 over T2 minus T1, which is equal to, well, this is approximately 60, and that's about 45, let's say. And the time interval is 1/2 and 0. Okay, so if you calculate that, you get 30. Now you may want to put units on this. In this case, the temperature is given by degrees Celsius, and the time is in seconds, let's say, so the units would be degrees Celsius per second. Okay, but that's not our focus here. All right, so we could take a linear function now and ask, what is the rate of change of that function over a certain time interval? Well, here's the same data from the previous slide, and I fit a line of best fit to the data, and I can ask, how is this line or is this linear function changing over a certain time interval? Well, let's pick a time interval, so let's pick 2 to 4, let's say. So this would be my time 1 and my time 2. Then I find my corresponding capital T. Let's say that's at 100. That's T1. And this one is at about 160. That's my T2. And then the rate of change, again, is just the change in T, capital T, over the change in small t, which is equal to T2, capital T2, minus capital T1, over T2 minus T1. And in this case, this is just 160 minus 100 over 4 minus 2. If you evaluate that, you get 30. But what I'd like for you to pay attention to is what's going on. The difference between small t2 and t1 is this right here, while the difference between the two temperatures is this right here. So in fact, what I'm doing when I'm calculating the average rate of change of a linear function is just finding the slope of that function. So I can answer this question now. The answer is its slope. Okay, so we don't only have to consider linear functions to find the rate of change. We could also find the average rate of change of an arbitrary function. So for example, here we have a quadratic function. I could find the average rate of change over an interval, let's say x1 to x2, like this, then I need to find f of x1 and f of x2, like this. Then the average rate of change over the interval x1 to x2 is just the change of f on that interval over the change in x, which is equal to f of x2 minus f of x1. That's over x2 minus x1. Okay, and that's whatever values it happens to be. But what I want to focus on is the geometry of the situation. Similar to the previous slide, the difference in x1 and x2 is this here, while the difference between f of x1 and f of x2 is this here. So when we're finding this, we're actually finding the slope of what's called a secant line, which is a line that passes through these 2 points. Okay, secant line. Okay, so the average rate of change of a function, f of x, over the interval x1 to x2 is the slope of the secant line through the points x1 f of x1 and x2 f of x2. Okay. What I want you to notice here is that this average rate of change is a very coarse description of the function. So pretend that this function is representing the velocity of some object. Well, if you look at this point, the object is actually decelerating, even though over this interval the average rate of change is positive. Right here it's decelerating, so the rate of change somehow in this part is negative. So is there a way that we can get a better idea of what the function is doing close to a point, close to a moment in time? Well, there is, in fact. What we could do is start drawing secant lines through points, through a point that we're interested in, and points that get closer and closer to that point. So, for example, here's our coarse approximation from before. I could have a slightly better approximation if I pick this point. Okay. Here's the corresponding secant line. I could get an even better one here, something like this, let's say. Or an even better one if I go through here, like this. Right? So as this point gets closer and closer to this point, this secant line more accurately describes what the function is doing at that point. This is a key observation. Take a look at this demonstration I whipped up on Desmos. Here's our function and our secant line. Here's the point we're interested in, so we want to know what the function is doing at this point or near this point. And here's the other point of our secant line. Watch what happens. I'm going to move this point closer and closer to this point, but watch what happens to the secant line. The slope is changing, but you notice the secant line is getting to be a better and better approximation for that function at that point. You see, the function is decreasing here, the secant line is also decreasing. And if we were to zoom in, you would see that the function and the secant line are very close. They look very, very similar. In fact, if I were to make the points even closer, zoom in a bit more, you can almost not tell the difference between these two at that point. we call the average rate of change over a small interval that keeps on getting smaller the instantaneous rate of change. Moreover, as that interval gets smaller and smaller, that secant line, which goes through 2 points on the function, approaches what's called a tangent line, which is a line that goes through only 1 point of the function. The slope of this tangent line is the instantaneous rate of change. So that's a more formal way of phrasing this first statement. Now this is a key concept in this course, and we have another name for it, which is the instantaneous rate of change of the function f of x at the point x1, f of x1, is called the derivative of f of x, the function, at the point x1. That's the topic of the next lesson.